The Luftwaffe's intelligence officers had grown accustomed to dismissing Allied innovations as exaggerated propaganda by early 1944. Reports filtering through occupied Europe spoke of British fighters carrying batteries of rockets beneath their wings, supposedly capable of sinking destroyers and demolishing concrete bunkers. German analysts laughed off these claims in briefing rooms across northern France. Rocket projectiles had appeared in previous wars with limited success. The Soviets experimented with Katyusha systems, certainly, but mounting such weapons on single-engine fighters seemed absurd. The physics alone suggested wild inaccuracy. How could a pilot possibly aim whilst managing recoil forces from 8 simultaneous launches? The Wehrmacht's technical staff filed these reports alongside other Allied bluffs, confident their panzer divisions and coastal fortifications remained immune to anything short of heavy bombing raids. That confidence shattered on the morning of 18th March 1944, when Typhoon fighters from 609 Squadron swept over a German convoy near Abbeville. 60-pound warheads struck with such concentrated violence that entire lorries disintegrated mid-road. Survivors stumbled from burning wreckage, unable to comprehend what weapon had just torn through their column. No bomb craters marked the tarmac. Instead, vehicles had been pierced clean through, fuel tanks ignited, ammunition stores detonated in chain reactions. Wehrmacht, after action reports filed that week, struggled to categorize the attack. Commanders initially suspected specialized anti-tank guns mounted on aircraft, perhaps some derivative of the 2-pounder cannon. The reality proved far more unsettling. Royal Air Force Typhoons had begun operational deployment of the rocket projectile Mark III, a weapons system that would redefine ground attack aviation before the year ended. German skepticism stemmed from legitimate technical concerns. Traditional aircraft ordnance followed predictable ballistic paths. Bombs fell according to gravity and airspeed. Cannons fired along fixed trajectories. Rockets introduced chaotic variables. Motor burn rates fluctuated with temperature. Rail alignment shifted under G-forces, and wind conditions affected unguided projectiles far more than streamlined bombs. Luftwaffe test programs had explored similar concepts in 1942, mounting Werfer Granite rockets on Focke-Wulf 190s with disappointing results. Accuracy proved abysmal beyond 300 meters, and the additional weight compromised dogfighting capability. German engineers concluded that rocket armament suited desperation, not doctrine. Why would the RAF, already fielding superior Spitfires and Mustangs, burden their fighters with such primitive weapons? The notion seemed tactically backwards, a sign perhaps that British industry had exhausted more sophisticated options. This fundamental misunderstanding cost the Wehrmacht dearly throughout the spring of 1944. Whilst German analysts dismissed rockets as inaccurate novelties, RAF squadrons refined their employment into lethal science. The key lay not in precision but in saturation. A single Typhoon carrying 8 rockets could blanket a target area equivalent to a heavy cruiser's broadside. 4 aircraft attacking in sequence delivered 32 warheads within seconds, overwhelming even hardened positions. Coastal batteries that had withstood months of strategic bombing found themselves defenseless against these new tactics. Reinforced observation posts crumbled as solid fuel motors drove penetrator heads through meters of concrete. Ammunition bunkers, designed to resist 500-pound bombs, exploded when rocket warheads found ventilation shafts and blast doors. The psychological effect matched the physical destruction. German troops had learned to endure conventional air raids through drills and shelters. Rockets offered no such comfort. Their approach gave minimal warning, no crescendo of falling bombs, just the terrifying shriek of Napier Sabre engines, followed by instantaneous impact. Survivors described the sound as tearing fabric amplified 1,000-fold, a noise that bypassed rational thought and triggered primal fear. Entire infantry companies abandoned prepared positions after witnessing rocket strikes, convinced that no fortification could protect them. Morale reports from 7th Army headquarters throughout April documented spreading panic amongst frontline units. The weapon the Luftwaffe had mocked as propaganda now dominated tactical planning across occupied France. The rocket projectile. Mark III represented 18 months of accelerated development by British ordnance engineers confronting an urgent tactical problem. By mid-1942, RAF planners recognized that existing armament, machine guns and 20mm cannons, lacked sufficient punch against hardened targets. Bombing accuracy remained frustratingly poor, even with skilled pilots, and delayed fuse bombs often buried themselves uselessly in soft ground. The Admiralty had already fielded ship-launched rockets for anti-submarine work, suggesting a proven technology, ripe for adaptation. What emerged from trials at the projectile development establishment combined brutal simplicity with devastating effect. A 60-pound assembly comprising a 25-pound armor-piercing warhead mated to a 3-inch diameter solid fuel motor. The warhead itself borrowed design principles from anti-tank shells. Engineers fashioned a hardened steel nose cone capable of penetrating 14 inches of concrete or 5 inches of armored plate at impact velocities exceeding 1,000 feet per second. Behind this penetrator sat 11 pounds of Amatol high explosive, sufficient to generate catastrophic overpressure within enclosed spaces. The charge detonated via a base fuse timed to function after penetration, ensuring maximum destructive force occurred inside the target rather than against its exterior surface. This design philosophy diverged sharply from conventional bombs that relied primarily on blast effect. The RP-3 killed through perforation and internal explosion, turning bunkers into pressure chambers and armored vehicles into fragmentation grenades. Propulsion came from a cordite motor packed inside the tubular body. 19 pounds of solid propellant burned for approximately 1.6 seconds, accelerating the complete assembly from 0 to 1,500 feet per second across a burn distance of roughly 400 yards. The motor casing doubled as the projectile's airframe. 3 stabilizing fins welded to the tail section provided gyroscopic stability during powered flight. Unlike liquid fuel systems requiring complex pumps and valves, the cordite motor needed only an electrical igniter, dramatically simplifying installation and maintenance. Armourer crews could reload a Typhoon's full complement of 8 rockets in under 20 minutes, a logistical advantage that proved crucial during sustained operations. Rail launchers beneath the wings converted chemical energy into kinetic delivery with elegant mechanical simplicity. Each rail measured 5 feet in length, angled slightly downward to compensate for the Typhoon's attack dive geometry. Spring-loaded clips held the rocket in place until firing. Pilots triggered launches via a thumb button on the control column, sending electrical current through weatherproof cables to the igniter squibs. The system permitted selective firing, individual rockets, pairs, or full salvos according to tactical requirements. Most pilots favored the 8-rocket ripple, launching all projectiles within a half-second interval. This technique created a shotgun pattern approximately 30 yards across at typical combat ranges, dramatically increasing hit probability against point targets whilst ensuring at least some warheads struck larger installations. Ballistic performance depended critically on launch parameters. Optimal results occurred when pilots initiated dives at 4,000 feet, building airspeed to 350 miles per hour before firing between 1,200 and 800 feet altitude. This profile balanced accuracy against anti-aircraft exposure. Higher releases scattered projectiles across excessive areas, whilst lower attacks gave ground gunners lethal opportunities. The rocket's unguided trajectory followed a descending parabola after motor burnout, impacting roughly 1,000 yards forward of the launch point. Crosswinds introduced lateral drift, temperature variations affected propellant burn rates, and even humidity influenced flight characteristics. Pilots learned to compensate through experience, adjusting aim points based on conditions no instrument could measure. Manufacturing the RP-3 demanded enormous industrial coordination. Filling factories produced the Amatol explosive under hazardous conditions. Several plants suffered detonations during production, killing dozens of workers. Cordite mills operated at maximum capacity, diverting propellant from artillery shell stocks. Steel mills forged warhead casings to exacting specifications. Variations in metal composition affected penetration performance unpredictably. By late 1943, British factories delivered over 50,000 rockets monthly, a production surge that equipped 26 Typhoon squadrons by D-Day. Each rocket cost approximately £12 to manufacture, making them economically viable compared to the hundreds of pounds required for precision-guided weapons developed later in the century. The Hawker Typhoon entered service in 1942 as a high-altitude interceptor designed to challenge the Focke-Wulf 190 menacing British coastal towns. Its massive Napier Sabre engine, a 24-cylinder behemoth generating over 2,000 horsepower, promised the speed necessary to catch German raiders. Reality proved disappointing at altitude. Structural failures plagued early production models, tail sections literally tearing away during high-speed dives. Engine reliability remained abysmal through 1943, with cylinder sleeves cracking under stress and coolant systems failing unpredictably. Fighter commands seriously considered cancelling the entire program by spring 1943, viewing the Typhoon as a costly failure, absorbing resources better spent on proven Spitfire variants. Salvation arrived through accidental discovery rather than intentional design. During low-level combat trials against ground targets, test pilots noticed the Typhoon excelled at precisely the mission it had never been intended for. That enormous engine delivered breathtaking acceleration below 5,000 feet, where air density maximized power output. Thick wings, a liability at altitude, provided stable gun platforms during strafing runs. The aircraft's brutal strength, initially problematic for dogfighting, became advantageous when absorbing ground fire damage. A Typhoon could return to base with cylinders shot away, control surfaces shredded, and fuselage punctured by flak fragments that would have downed lighter fighters. By summer 1943, Fighter Command quietly repurposed its troublesome interceptor into Britain's premier ground attack platform, a transformation that required extensive modification. Installing rocket rails demanded significant airframe engineering. Each wing needed to support 4 launch rails plus the combined weight of 4 60-pound rockets, an additional 240 pounds per side. Structural reinforcements strengthened wing spars at the attachment points, preventing fatigue cracks under repeated launch stresses. Engineers positioned the rails outboard of the landing gear to avoid exhaust blast damage during firing. Electrical wiring snaked through wing cavities, connecting cockpit firing buttons to individual rocket igniters. The modification added approximately 600 pounds to the Typhoon's empty weight, reducing maximum speed by roughly 15 miles per hour, an acceptable trade-off for the firepower gained. Hawker Aircraft's modification centres processed existing Typhoons at a rate of 30 aircraft weekly by January 1944, whilst new production incorporated rocket capability from the assembly line. Pilots transitioning to the rocket-armed Typhoon faced a steep learning curve. Traditional fighter training emphasized deflection shooting and energy management for air-to-air combat. Ground attack required entirely different skills: dive angle calculation, altitude awareness under intense concentration, target motion prediction against moving vehicles. The RAF established specialized courses at the Armament Practice Camp in Fairwood Common, where pilots spent 3 weeks mastering rocket employment. Training began with static ground targets, derelict lorries, and mock bunkers positioned on coastal ranges. Instructors emphasized the critical importance of dive geometry: too shallow, and rockets scattered wildly; too steep, and the aircraft risked flying through its own fragmentation pattern or striking the ground during pullout. Live fire exercises consumed thousands of practice rockets monthly. Pilots discovered that the weapon demanded counterintuitive techniques. Unlike bombs that required precise release timing, rockets needed steady aim during the entire firing sequence. Any control input during launch, a twitch on the stick, rudder adjustment for wind, scattered the salvo unpredictably. The best marksmen learned to establish their dive, trim the aircraft perfectly, and fire whilst maintaining absolute steadiness for the half-second launch duration. Wind conditions complicated matters enormously. A 20-knot crosswind could drift the entire pattern 30 yards laterally at typical combat ranges. Experienced pilots began reading smoke, dust, and vegetation movement to estimate wind strength, adjusting their aim point accordingly without conscious thought. Operational squadrons developed launch techniques through bitter trial. Early attacks saw pilots firing from excessive altitude to avoid flak, achieving negligible accuracy. Losses mounted as squadrons pressed lower, seeking the sweet spot between effectiveness and survival. By March 1944, doctrine settled on the 1,200-foot release altitude as optimal, low enough for accuracy, high enough to permit escape maneuvers. Squadrons adopted the cab rank system, with 4 aircraft flights orbiting above battlefields awaiting ground controller direction. When targets appeared, the flight leader rolled into his attack dive, followers spacing themselves 15-second intervals behind. This sequence delivered 32 rockets across a target area within 1 minute, overwhelming defensive reactions whilst minimizing mid-air collision risks during the vulnerable pull-out phase. The Falaise Pocket became a killing ground of such intensity that veterans struggled to articulate its horror decades later. By mid-August 1944, German 7th Army and 5th Panzer Army found themselves trapped in a rapidly constricting corridor southeast of Caen. Field Marshal von Kluge's forces, some 50,000 troops with remnants of 9 panzer divisions, attempted desperate breakout towards the Seine, whilst Allied ground forces tightened the noose from north and south. The single escape route funneled through narrow roads between Falaise and Argentan, creating a concentration of military vehicles unmatched anywhere in the European theatre. Typhoon squadrons from the 2nd Tactical Air Force circled overhead, like predators scenting blood. Their rocket rails loaded with salvation for Allied ground troops and annihilation for everything German below. Reconnaissance flights on the morning of 13th August revealed the scale of opportunity. Columns stretched bumper to bumper for 15 miles, Tiger tanks interspersed with half-tracks, supply lorries, horse-drawn artillery, even commandeered French civilian vehicles packed with fleeing soldiers. Luftwaffe fighters had effectively ceased to exist over Normandy by this point, their bases overrun, or fuel stocks exhausted. Cloud cover sat at 6,000 feet, perfect for masked approaches. Wing Commander Charles Green, leading 123 Wing from forward airstrips near Bayeux, recognized immediately that conventional tactics would prove insufficient. His operations officer calculated that even with every available Typhoon flying maximum sortie rates, they could not destroy the column through individual attacks before darkness allowed enemy dispersal. Green ordered mass formation strikes, entire squadrons attacking simultaneously rather than the standard 4 aircraft flights. At 2:30 that afternoon, 16 Typhoons from 181 and 247 squadrons rolled into near vertical dives above the Tronchambois Road. 128 rockets launched within 20 seconds, the combined ripple visible from Allied observation posts 12 miles distant. The initial salvo struck an ammunition convoy near the column's center, secondary explosions propagating outward as lorries loaded with artillery shells detonated in chain reactions. Burning vehicles created roadblocks that trapped everything behind them, whilst forward elements accelerated desperately, colliding with slower traffic ahead. Within 5 minutes, organized retreat had devolved into panic. Flight Lieutenant Herbert Pring described his third pass that afternoon in a 1946 interview with RAF historians. Smoke had become so dense that he selected targets purely by thermal signature through the haze, bright spots indicating engine blocks still radiating heat. His salvo caught a Panther tank attempting to escape across a wheat field, 2 rockets striking the turret ring, whilst a third penetrated the rear deck. The tank continued rolling for another 30 yards before catastrophically exploding, the turret cartwheeling skyward in a pillar of flame. Pring noted grimly that by his 4th sortie he could no longer distinguish individual vehicles. The entire corridor had merged into one continuous bonfire, and his rockets simply added to the conflagration. Ground crews at his forward airstrip counted 14 separate shrapnel holes in his Typhoon's wings, evidence of how close pilots pressed their attacks. German survivors' accounts corroborate the devastation from below. Hauptmann Erich von Luck, commanding a Kampfgruppe from 21st Panzer Division, recorded that rocket attacks made organized movement impossible after midday on the 13th. His Tigers, nearly impervious to most Allied anti-tank weapons, proved helpless against warheads striking from above. One rocket penetrated his command tank's engine deck, igniting fuel and ammunition simultaneously. Von Luck escaped through the driver's hatch seconds before the internal explosion blew the turret 50 feet from the hull. He estimated his unit lost 60% of its armor to air attack before reaching Allied lines, where ground forces mopped up the stunned survivors. The massacre continued for 3 days. Typhoon squadrons flew up to 6 sorties daily, pilots returning to forward strips, refueling in under 10 minutes, and launching again whilst armourer crews manhandled fresh rockets onto wing rails. Exhaustion claimed lives as surely as flak. Several pilots fell asleep during landing approaches, crashing short of runways. Squadron leader John Baldwin recorded in his logbook that by the 16th, target selection had become meaningless. Every road, every field, every tree line concealed burning wreckage. His final sortie that day expended all 8 rockets into a forest where infrared signatures suggested hidden vehicles, but post-strike reconnaissance proved impossible through the smoke. Allied armies advancing through the pocket days later discovered carnage beyond military precedent. An estimated 10,000 vehicles destroyed, 5,000 horses dead in harness, and German casualties exceeding 40,000. Operation Plunder demanded perfection in timing and coordination beyond anything attempted in the European campaign. Field Marshal Bernard Montgomery's plan to cross the Rhine, near Wessel on 23 March 1945 involved pushing the British Second Army and 9th United States Army across a river that had defended Germany's industrial heartland for centuries. German defenders held every advantage geography could offer: elevated positions on the eastern bank, clear fields of fire across the water, and months to prepare fortifications. Intelligence estimates identified over 300 flak positions within 5 miles of the crossing sites, ranging from 88mm heavy guns to quad-barreled 20mm cannon platforms. These installations could shred assault boats and pontoon bridges within minutes unless neutralized before the first troops embarked. Air Marshal Arthur Coningham, commanding 2nd Tactical Air Force, assigned the counter-flak mission exclusively to Typhoon wings. Heavy bombers lacked the precision necessary to avoid cratering the very ground Allied engineers needed for bridgehead construction. Medium bombers required clear weather that March's temperamental conditions could not guarantee. Only rocket-armed fighters could deliver pinpoint destruction regardless of visibility whilst preserving infrastructure. Coningham allocated 16 squadrons, 192 aircraft, to systematic suppression beginning 72 hours before H-hour. Each flak position received individual attention in a target catalogue that read like a deadly phone directory. Map coordinates, estimated gun type, protective construction details, approach vectors that minimized exposure to neighboring positions. The suppression campaign commenced at dawn on 20th March with clinical efficiency. Squadrons operated in rotating cab rank patterns, ensuring constant Typhoon presence over the battle zone. Forward air controllers embedded with Royal Artillery observation posts directed strikes via VHF radio, talking pilots onto targets obscured by morning mist. Flight Lieutenant James Kyle from 197 Squadron recalled his briefing that morning. A precise grid reference, the warning that the position housed an 88mm gun behind 3 feet of reinforced concrete, and the laconic instruction that it must not survive to see H-hour. Kyle's flight approached from the south at 4,000 feet, rolled inverted to acquire the target